Hi everyone. Today we are going to see a topic of balanced search tree in design and analysis of algorithms. So before letting into the topic, first, what is binary tree? Binary tree means a tree must have only two nodes. And what is binary search tree? So binary search tree is nothing but compared with the root node, the smaller element should be on the left side and greater element should be on the right side. So this is the binary search tree. Now, what is balanced search tree? So a balanced search tree is nothing but it not only to maintain its order between the nodes, that is left and right node, it also have to control its height even after the insertion of any element and also deletion of any element. So you should maintain its height also in addition with the order of the nodes. And to maintain its height, that is to control its height, it must rebalance after insertion and also after deletion of any node. So rebalance is to be done. So while doing this rebalance, it may cause a computational overhead and it may complicate the algorithm for insertion and deletion. So we are going for a balanced binary search tree. So it is nothing but a balanced binary tree is also called as height balanced tree. So what is height balanced tree is after inserting a new node or deleting any node, the height should be adjusted in such a position. So it is defined as a binary tree in which the difference between height of left and right subtree should not be more than 1. So how to find the height of the tree? Height of the tree is nothing but the number of edges on the longest path between root node and leaf node. So consider this example. Here N1 is considered as a root node and these three nodes, that is N4, N7 and N6, is called as leaf node. So to find height of the tree, we have to check with either in the left side or in the right side the longest path. So from the root to the right, a leaf, only 2 edge. Consider left side from the root to the leaf. We have 3. So the height of the tree is 3. So for this tree, the height is 3. That is longest path between root node N1 to the leaf node N7. So a binary search tree is a tree in which each node on the left side has a lower value than its parent node and node on the right side should be the higher value compared with this parent node. So this is the main condition to satisfy the binary search tree. Why we need a balanced binary tree here is it provides searching more faster than the linear tree data structure. So for searching any element, balanced binary search tree is very useful. So see this example. Here N1 is the root node and N4, N5 and N6 is the leaf node. So the number of hops required to search an element 79. So if we want to search an element 79, the number of hops to search is 2. And maximum number of hops required to search any element is also 2 maximum. So if I want to search this element, number of hops is 2. If I want to search this element, number of hops is 2. So same like for this element also number of hops is 2. So the maximum number of hops for this tree is 2. So the average cost to search the element is order of log n. But consider this case. In this case, so the number of hops required is 5. So it is the worst case complexity of order of n. How many number of nodes are there? You have to search that much time. So the worst case complexity is order of n. So to avoid this condition, computational overhead, we are going for a balanced binary search tree. That is AVL tree. So AVL tree is nothing but a self-balancing binary search tree where the difference between height of the left and height of the right tree of any node cannot be more than 1. So the main rule behind AVL tree is the difference between height of the left tree and height of the right subtree, which cannot be more than 1. So it was founded out by Adelson, Wilsky, Landay. So the name is the first letter is A, V and L. So it is named after its inventors, AVL. So the difference between height of the left subtree and right subtree of any node is known as balance factor of the node. So if you want to say the tree is said to be balanced, so the balance factor of the each node is between -1 to 0. That is, it may be either -1 or 0 or 1. Then the tree will be balanced. If it is greater than that, then the tree will be unbalanced. So we have to balance the tree accordingly. So the formula to calculate balance factor is height of left of subtree minus height of right subtree. So this is the formula to calculate balance factor. After calculating that, the balance factor should lie in between -1 to 1. If it is not, we have to again rebalance it. So if the balance factor of any node is 1, it means that the left subtree is one level higher than right subtree. If balance factor of any node is 0, it means both right subtree and left subtree is of equal height. If balance factor of any node is -1, then it means that left subtree is one smaller than right subtree. Okay. So consider this example. We have A, B and D is in left side and C is right side. So to find out balance factor, the formula is height of the left subtree minus height of the right subtree. Height of the left subtree is 2 and height of the right subtree is 1. So 2 minus 1 is 1. So balance factor for this node A is 1. If you want to find a balance factor for B, height of left is 1, right is 0. So 1 minus 0 is 1 for this. For leaf node, it is 0. So AVL tree, it controls the height of the binary search tree by not letting it to be skewed. That is, it won't give the worst case complexity of order of n. We'll do the rebalancing of the nodes. So the time taken for all the operation in a binary search tree of height is order of h. That is, for height is order of h. It can be extended to order of n if the binary search tree becomes skewed. So that is worst case. In the worst case condition, the binary search tree may be of order of n. So by limiting its height to log n, AVL tree imposes an upper bound on each operation to be order of log n. N is nothing but the number of nodes present in a given tree. Next, consider this example. This is a self-balancing binary search tree, that is AVL tree. So all the leaf nodes balance factor is 0. If I want to calculate balancing factor for 75, then it is left minus right, 0 minus the 1 minus 1 is 0. If you want to calculate for this, left is 1 and right 2 edges 2. So 1 minus 2 is equal to -1. If I want to calculate for root node, 3 is the maximum height on the left side and 2 is the maximum height in the right side. So 3 minus 2, 1. So this is how we have to find the balance factor. So the complexity analysis is, if I take space, the average case analysis and worst case analysis order of n. If I am using for search operation, then it is order of log n for both the average case and worst case. If you want to insert or delete an element also, order of log n in case of AVL tree. So next we are going to see about operations on AVL tree. So AVL tree also perform the operation as such as binary search tree only, but if here the balancing factor is not -1, 0 or 1, we have to rebalance it. So, however, insertion and deletion are the operations which can violate this property, so they need to be revisited. So these are the functions of AVL tree. So inserting a new node or deleting a node and last displaying a node. So insert, left rotate or right rotate. Same as deletion also, left rotate and right rotate. As we have seen in a binary search tree traversals. So to display it, we have three types: pre-order, in-order and post-order. So first one is insertion. Insertion is nothing but if you want to insert any new node into a given tree, it is an insertion. After insertion, if it violates the property, we have to apply the rebalancing. We have to do rebalancing. Deletion also same way. We can delete any node from a node and we have to perform the rotation. That one we are going to see now. So here for insertion and also for deletion, any element is not balanced, we have to perform AVL rotations. Okay, so AVL rotation, when to perform AVL rotation is if the balancing factor is other than -1, 0 or 1. Here we have to perform four types of rotations. So first one is LL rotation, that is left rotation. It is nothing but inserted node is in the left subtree of A. That is LL rotation. If I want to insert, here I have one node. If I am inserting one left and again I am inserting left, this is LL rotation. Okay. Next, RR rotation is nothing but inserting a node in the right subtree of right subtree. This is RR rotation. LR rotation is inserted a node is in the right subtree of left subtree of A is LR rotation, left right rotation. That is, if I am having node, first one is left, so inserting on the right subtree of left subtree of A. This is LR rotation. RL rotation is just inserting a node in the left subtree of right subtree of A is RL rotation. So this first two rotation LL and RR is called as single rotations and RL and LR is called as double rotation. So when to perform LL rotation is when binary search tree become unbalanced due to node is inserted into the left subtree of any node, then we have to perform LL rotation. That is, it is clockwise rotation having balance factor of 2. So see this example, LL rotation. So if I am inserting A here, so here is balance factor is 0 for this one, for this the balance factor is 2. So this case we have to apply LL rotation, just one clockwise rotation. So B now becomes a root node, A is the left child and C is the right child. Now check the balancing factor, it is balanced. Same as RR rotation. When to apply RR rotation is if a node is inserted into the right subtree of A, then we have to perform RR rotation. It is an anti-clockwise rotation. If the balancing factor is -2, we have to perform the RR rotation. So now we have to shift this A as root and B as left node and C as right node. Next, LR rotation is double rotation. So it is nothing but first one is RR rotation and second one is LL rotation. We have to perform two rotations in case of LR rotation. First one is RR and second rotation is LL rotation. See, in this example, LR rotation. First one is we have to perform RR rotation. So RR rotation is nothing but we have to perform one anti-clock shift. then the node became, then the tree becomes like this. So now this is LL rotation. LL rotation is nothing but one shift clockwise rotation. Now it is balanced. So this is LR rotation. First one anti-clockwise, then clockwise rotation. Next RL rotation is left rotation plus right rotation. So this is the case for RL rotation. So if I am inserting a node in the right side of the A and left side to B, it is RL rotation. First we have to perform one clockwise, then it becomes RR rotation, then you have to perform one anti-clockwise rotation. Now we are going to look into an example. 10, 15, 9, 12, 13, 79, 45, 36. First one is 10. So 10, just 10. Now number is 15. 15 is greater than 10. So we have to insert here. Now we have to check the balancing factor. So balancing factor, now it is 0, left to minus, right? So for 10 it is minus 1. Next we are going to insert 9. So it is smaller. So we can insert 9 here. Now it's not a problem because it is 0 and here also 0. Now I am going to insert element 12. Compare with 10. 12 is greater. So it should come here. Compare with 15. It should be smaller. So it should be here. So likewise, while inserting each and every element, we have to check from the root node. So first inserting 10, no problem. Next inserting 15, tree is balanced. We are going to insert 9, now also 0. Now we are going to insert 12, 12. Okay, now also here 0, leaf node 0. Here left minus right, left is 1. So 1, here 1 minus 2, so minus 1. Next I am going to insert element 13. 13 compare with 10, it is greater. Compare with 15, it is smaller, but compared to 12 it is greater. So if while inserting 13, now see here it is trees imbalance. So now you have to perform rotation here. What is this? This is LR rotation. So first you have to perform one RR, then LL rotation. Okay, then you will get the tree like this. So 10, 9, 13, 12 and 15. 13 will become root node and 12 is the leaf node and 15 is the, 12 is the left node and 15 is the right node. Now the tree is balanced. Now I'm going to insert 79. Now if I inserting 79, see here it is 0, 0, 0, no problem. Here also no problem. Here 1 minus 2 minus not a problem, but check here it is 10. So while inserting 79, 10 become unbalanced. So you have to take this 3 nodes and you have to perform rotation. So it is RR rotation. Just RR rotation is one anti-clockwise rotation. So just 13 becomes the root node and 10 become the leaf node, left node and 15 become the right node. Now check this 12. 12 is greater than 10. So it should be inserted here. So after inserting all the element, you have to check the binary search tree condition also. That is, every node should be compared with root node and the smaller element should be only in the left side and greater element should be in the right side. So after inserting all the element, you have to check once for the binary search tree condition also. Next, I am going to insert element 45. So while inserting 45, greater than 13, greater than 15, less than 79. So see here minus 2. So it is RL rotation. So just take this 45 as root node and 15 as left node and 79 as right node. Okay. Next I am going to insert 36. So 36 greater than 13. Compared with 45 it is smaller. Compared to 15 it is greater. So 36. So check for balancing factor 0, 0, 0, leaf node 0, here minus 1, not a problem. So here 2, 2, 2 minus 3, minus 1. So it is balancing factor condition. Next, I am going to insert 22. So insert 22 is greater than 13, less than 45, greater than 15, less than 36. So here again arises RL rotation. So you have to take this 22 as a root node, 15 as left child, and 36 as right child. Okay. So this is the condition for insertion. Next, deletion. If you want to delete any element from a tree, the first step is you have to find the element in the tree where it is and delete the node as same as binary search tree deletion. Here two cases are possible. First one is we can delete from the right subtree or delete from the left subtree. First, if you want to delete an element from right subtree, if balancing factor of node is plus 2 and balancing factor of node of left child is plus 1, then we have to perform LL rotation. If balancing factor of node is equal to plus 2 and balancing factor of node of left child is minus 1, then you have to perform LR rotation. If balancing factor is plus 2 and node of left child is 0, we have to perform LL rotation. So while deleting from right subtree, if it is minus 1, we have to perform LR, or else you have to perform LL for both the cases. So this is an example. So case 1 is we are deleting 40. So just deleting 40 here, you will get LL rotation. So LL rotation is nothing but one clockwise rotation. Next, we are deleting an element 40 again here. If I am deleting 40, then we will get LR rotation. So LR rotation is nothing but we have to perform one right rotation and LL rotation. This is case 2. Case 3, if I want to again delete element 40 from here, then we have to perform one LL rotation here. So same case for deleting from left subtree also. If the node of right child is plus 1, we have to perform RL rotation, or else both are RR rotation only. If it is minus 1 or 0, it is RR rotation in case of deleting left subtree. So here given example for left subtree deletion. If I want to delete an element 10, then if I am deleting this element 10, then it becomes RR rotation. This RR rotation is nothing but we have to take one anti-clockwise shift. Next, if I am deleting 10, this is RL rotation. So RL rotation, we have to take this to center and the tree became like this. Next, if I want to delete 10, then it performs RL rotation. So that's all about deletion at the same as binary search tree. So we know the structure of a node, right? So this node contains one key element and one left tree and one right node, and we have to maintain the height of the node. It is a main condition in AVL tree. So to write structure for this structure name is node and followed by curly braces, and here we have keys of integer type and left and right, that is of pointer type. So struct node star left and struct node star right, and height is of integer type. If I want to insert height of a node, this is the function to create height of the node. And we all know the maximum of two integer. This is the function to create maximum of two integer. Next, here it is new node creation. If I want to create a new node, first we have to allocate a memory. That is ML is memory allocation for that node is of structure type. We already defined the structure, and we have to define key. Left right should be first time it is null, and node of the height is 1 for the first time. So this is this. new node creation structure. Next, we have to check the balancing factor each and every time. The formula is left minus right. That is height of left subtree minus height of right subtree. If it is null, it must return 0. So this is a pseudocode for a left rotation. So look at this example. It is left rotation. So first y is equal to x of right? So y is nothing but x of right. And t2 is nothing but no t2 is y of left. Now we have to perform rotation. That is y of left is equal to x. Y of left. Which one is y of left? Y of left is nothing but a. So it becomes x now. And x of right is, this is t2. That is x of right, that is c is become t2. Right. So after perform rotation, we have to update the height. So x of height is height of left minus right, and same as y of height is y of height, left minus right plus 1. Same as for right rotation also, we have to first perform the right rotate, and then we have to perform rotation, and we have to update the height. And this is the pseudocode for inserting a node. If it is null, we just return no node is present. If it is less than, we have to insert in the left side. If it is greater, we have to insert in the right side. And each and after each and every insertion, we have to update the height. We have to get the balance factor. And this is the case for rotation. And these are the cases for rotation: right case, left case, right left case. And for deletion, the same binary search tree deletion. If it is null, then we have to return root. If it is less than, the key is less than root node, we have to check only with the left side. We have to traverse only with the left side and delete the given element. And if it is greater element compared with root, we have to traverse only through the right side and we have to update it. If there is no child, that is it is leaf node, we can directly delete the node. And if it has only one child, we can delete easily. If it is node with two children, we can delete, we can take the in-order successor. Yeah. Then the analysis for AVL trees for insertion and deletion, height also order of log n. This is the analysis for AVL tree. So AVL tree is nothing but it is a self-balancing binary search tree. It must maintain a balancing factor of -1, 0 or 1. If it is not, we have to do the rebalance by rotation. There's 4 types of rotations: LL rotation, RR rotation, RL rotation and LR rotation. Thank you.